Zoom. Oh. Is it working now? All good? Say again?
Minimize these settings.
Yeah, I'd like to remove that hide video panel. Okay, that's better, yeah. And the sound is all good?
Yes.
Online? Is it good? Okay. Okay, we still have a minute, so. Okay, tier 2. Continue, I guess. Okay, I think we can get started, right? Is there some holiday today? Normally there are more people in lecture. Okay, you're making it barely. Okay. Maybe we should just lock the door. They can still attend online. Okay. Yeah, today we're going to continue memory latency. Maybe the weather is so good, so everybody's outside hiking or doing something. Don't worry, you guys are not missing out. We'll talk more about memory latency. Last time we started this topic, if you remember well, we started low latency, and I'm going to talk about predictability. Hopefully tomorrow, memory controllers, etc., and probably next week. So we're going to be on this topic for some time. I was thinking of getting to memory controllers today, but I'm not sure if we will make it. Let's see. But everything we talk about is really about memory controllers in the end, even though we don't directly deal with exactly how the memory controller works. You can think that these low latency architectures depend on a memory controller doing the right thing to make sure low latency is achieved. But we're going to do a more rigorous treatment of memory controllers, hopefully tomorrow. Okay, and if you have questions, please feel free to ask. Last lecture, we discussed two major reasons for long memory latency. One is the design of the memory microarchitecture. In this case, DRAM. We're covering DRAM a lot, since that's the dominant memory technology that we have today. For about 60 years, it's been so. And it's unlikely to get replaced anytime soon. And we will also have a lecture on emerging memory technologies later. So hopefully it'll be interesting. We've covered a lot the reason one. But today we're going to focus more on the reason two, which is how much latency are we really wasting in the way we actually treat our memory devices today. Basically, today we have a one-size-fits-all approach to latency specification. And we've started covering this briefly, if you remember in the last lecture. Basically, you have reliable operation latency. That's actually very heterogeneous across devices, across temperatures, across chips, across different parts of a chip, across different voltage levels. But today, we don't exploit that. Basically, what we do today is decide on one latency parameter for a given device or a given set of devices, and then access everything with that parameter. But we could actually be much more efficient in terms of both performance as well as energy, as you will see, if you could dynamically find out, or statically or dynamically find out, the lowest latency you can reliably access a memory location with. So we're going to see instances of this, and then we're going to gradually move to using latency characteristics of devices for security. We've kind of talked about that when we talked about processing in memory, memory-centric computing, but I think this is an important area that I would like to emphasize. So I'm going to spend some time on taking advantage of the latency characteristics to enhance security of systems. Does that sound good? I think it's a very interesting area. Okay, so basically the takeaway is we would like to find sources of latency heterogeneity and exploit them to minimize latency or create other benefits. Clearly, this will complicate some things. This will complicate testing, complicate memory controls, etc. But hopefully the benefits will be commensurate. As I said earlier, no pain, no gain, right? If you don't change anything, you're not going to gain much. Okay, so this is a slide that I showed in the last lecture. Basically, we have latency variation in manufacturing and operating conditions. Where we have variation in manufacturing and operating conditions, and that leads to variation in timing parameters, latency variation essentially. So some DRAM chips may have cells that are actually quite strong. Some other DRAM chips may have cells that are actually not so strong. So the latency to access the not so strong cells need to be high. The latency to access the strong cells does not need to be as high. But what essentially within a DRAM chip, there are also slow cells and fast cells, and we're going to see more why cells could be slow or fast soon. But you could imagine, right? You could have a weak access transistor that makes things slower, etc. So there's a lot of latency variation in the reliable operation latency, but today we don't take advantage of it. Meaning DRAM standards keep one latency. So even though there's a lot of variation, the standard latency is chosen so that it's very high. And the reason is we want to make all of the devices acceptable. That is good for DRAM business, right? That way you don't throw away chips that do not satisfy this maybe very aggressive standard latency. If you had chosen the standard latency somewhere over here, a lot of the chips would not satisfy it. How do you make them satisfy it is a different question, of course, right? It may not be easy. So people choose a standard latency to be relatively high so that a lot of chips comfortably fall into that latency variation. And as a result, you don't need to discard the chips. Make sense? Okay. So, okay, now let's talk about what caused the long memory latency. We have covered actually until here, but I hadn't covered this slide. Essentially, this choice that I have just shown you over here leads to conservative timing margins, right? You have some latency, essentially timing. It's very conservative. It's set to cover the worst case in a sense. And worst case is worst case devices as well as worst case temperatures. So you want to operate a device at the maximum temperature that the standard suggests. It's 85 degrees, 95 degrees. In automotive systems, it's 105 degrees, maybe even higher, even in stringent systems, because these are going to be out in the field, right? And actually, there needs to be special precautions taken for DRAM that's designed for automotive, etc. So it depends on what is the specification. But again, it's worst case. The latency doesn't change if you're operating in the common case. Maybe the common case you're operating at 30 degrees Celsius, right? Okay. The goal is to enable a wide range of operating conditions, of course, to set by setting the latencies to worst case. And then there's worst case devices. DRAM cell with the smallest charge across any acceptable device determines your latency. And the goal is really to tolerate process variation at acceptable yield in this case. But because of at least these two, we have large timing margins for the common case, assuming the common case temperature is lower than the worst case, and assuming the common case device doesn't have that bad cells, let's say. Okay, so this is what we wanted to understand and exploit in a lot of our works. Now let's take a look at how cells are affected by this. So you've seen this picture before, so it's going to be a quick overview. Essentially, DRAM stores data as charge. You have two-dimensional array of cells. This is a subarray, if you will, or a bank, depending on your abstraction level. But keep it as subarray for now. Essentially, you need to access the DRAM cell and you need to amplify the data. To be able to do that, you need to first activate the row, which essentially enables the sensing of the cells through the sense amplifiers by connecting the bit line to the sense amplifiers. And then sense amplifier kicks in and restores the charge. There's a charge restoration. So all of these take time. Sensing takes time. Charge restoration takes time. And then pre-charging so that you can enable the subarray or the bank for the next access takes time. Makes sense, right? And we've seen all of these in the last lecture. And we've seen ways of reducing these by changing the DRAM microarchitecture. Now let's take a look at this from a simulation perspective. If you actually simulate one DRAM cell connected to one sense amplifier, this is what the charge of the cell looks like over time. Initially, assume the cell is charged. Sense amplifier is initially pre-charged, meaning it's half VDD, as you can see. In the best case, cell is complete VDD, right, 100%, but that may not be true depending on when you access the cell. So keep that in mind also. And then normally data is read as 1, assuming the value is over here. Data is read as 0, assuming the value is over here. And there's some sensing margin, as you see over here. You always need to have margin in analog devices so that you can convert analog to digital. So after you enable after you connect the cell to the bit line, what happens is a cell shares its charge with the bit line. So cell loses charge, and the sense amplifier starts kicking in. It starts amplifying that charge, and it starts restoring that charge at some point. So it kicks in at a higher level. And once the cell charge is restored, in theory, you should be able to access that cell, right? Actually, it's not exactly when it's completely restored. You could actually access the cell at a maybe 75% charge point over here. Makes sense, right? Okay, so you don't want to access the cell while it's being sensed by the sense amplifier, because that's unstable state. You want to access the cell when it's mostly restored, meaning while it's comfortably in this data 1 range. Make sense? Okay, but what people do in practice is they add a longer time to start accessing the cell. And this is what's the timing margin. Basically, there's a margin that's added beyond the, let's say, comfortable operating point of the cell, so that they can adjust for temperature, for example. There might be temperature variation. There might be variation across cells, etc. And there's a comfortable margin added. So you don't the standards add this margin so that you access the cell hopefully correctly. Makes sense. So we want to get rid of this margin as much as possible, because that margin is overhead, right? It's overhead in terms of latency. It's overhead in terms of energy. When you don't need it, of course. When you need it, that margin is good. When you don't need it, that margin is overhead. Okay, so why do we need the extra timing margin? We've kind of discussed this earlier. There's process variation and there's temperature dependence. Not all DRAM cells are equal. And if a cell can be accessed faster than some other cells, you have extra timing margin for that cell. And I'm going to call that cell a cell that can store a large amount of charge. This kind of an abstraction, right? Let's take a look at that. Basically, ideally, all cells should be equal, but we cannot make everything equal. There's variation. If all of them are equal, they have the same size, same charge level, maximum charge level, and same latency, and same characteristics, etc. But real life is very heterogeneous. Just like the retention times, latencies are also very heterogeneous, as you can see over here. Cells are of different size. As a result, they carry different charge. And as a result, they can be accessed with different reliable operating latencies. Now let's go into a little bit more detail over here. I'm going to call them small cells and large cells. But basically, the latency is really determined by the smallest cell, smallest acceptable cell, I should say. If you have large variation in cell size, you have large variation in charge, and as a result, you have a large variation in access latency. So let's go into a little bit more detail. What is a small cell? What's a large cell? It's not about small and large in the end. That plays a role into it, of course, like how large the capacitor is, how much charge it can actually store. That's really important. But it's not just the capacitor, actually. It's other things. I don't think I locked the door. So if you're, I heard something at the door. Okay, so people can still come in. Basically, whenever you want to access a DRAM cell, you enable the access transistor such that the capacitor gets connected to the bit line. And this is a more physically reasonable picture of DRAM. So clearly, cell capacitance, how much charge you can store over here, plays a role in terms of how fast you can access things. If there's a lot of charge, this charge movement is much faster, clearly. Contact resistance is important also, because if the resistance over here is high, you may not be able to move the charge. Even if the charge is large, you may not be able to move the charge quickly to the bit line. And then transistor performance is also important. If the transistor is slow, for example, for some reason, then again, you cannot move the charge to the bit line quickly. Right? So all of these have an interesting combination that affects the performance of the cell. I'll call, essentially, a cell may have the worst cell probably has low capacitance, high resistance, and low transistor performance, right? That's the worst cell you can have. But then it's not clear if that's the worst cell, right? A cell with terrible capacitance may be worse than a cell with bad, but not so terrible in all of these three characteristics. It's very hard to determine, hard to pinpoint all of these without testing every single cell at a much lower level than we can do today. Does that make sense? I think it's fascinating. And as things become smaller, some of these things become much more difficult to determine. Okay, but I'm going to call this poor cell a small cell. A small cell can store a small amount of charge. It'll have small cell capacitance, high resistance, slow access transistor. And as a result, it has high access latency. So hopefully this gives you some more insight into what's going on underneath. Okay, so that's process variation. We've discussed that. There's also temperature dependence, which is really orthogonal. And this is the fact that DRAM leaks more charge at higher temperature. We've seen this with retention time, right? At high temperature, the cells become much more leaky. And as a result, you need to refresh them more frequently. Today, DRAM has multiple operating modes. At low temperatures, below 85 degrees, you refresh cells every 32 milliseconds. At high temperatures, that number the refresh rate increases to every 16 milliseconds, right? At even higher temperatures, 110 degrees Celsius, et cetera, it could be 8 milliseconds, et cetera. Okay, so, but this affects latency also. Essentially, if you're operating at low temperature, you're operating, you have more charge, which means that you can access the cell faster. So this is another example over here. This is cool DRAM, let's say, room temperature. And at a high temperature, let's say 85 degrees Celsius, cells are leakier. Here you have small leakage, here you have large leakage on the right. And at high temperature, you have small charge. And at low temperature, you have large charge. This is independent of how small or large or how high performance or low performance your cells are. This is another reason why you have large variation access latency. Hopefully that's clear also. Right? How many people have read the paper that we have kind of covered in data retention time, which is the ISCA 2013 paper that determines the retention times of DRAM chips? Anybody yet? It's part of the homework, but maybe not yet. It's not a required one. But if you read that paper, it actually has a very nice graph that shows how retention time relates to temperature. It's a very predictable relationship. It's an exponential relationship. I think as you increase the temperature, every 10 degrees Celsius, retention time of a cell reduces, of an average cell reduces by about 46%. And you have a nice exponential curve. And then there's variation, of course, in that. So you can actually bound the worst case and best case cells as well. Okay, so it's similar to that. Essentially, what I've said over here, DRAM timing parameters are dictated by the worst case. The small worst case variation, meaning the smallest cell with the smallest charge in all DRAM products, I should say acceptable ones, operating at the highest temperature. So that's the worst case essentially, which means that this leads to large timing margin for the common case. So if you know all of this, I think developing an idea is relatively simple. And the idea in this work is called Adaptive-Latency DRAM. It's to optimize the DRAM timing at for the common case, meaning understand what temperature you're operating at currently, and understand the characteristics of your current DRAM module that you're using, and adjust the timing parameters based on that. Hopefully that makes sense. So why would this reduce latency? I think we've already discussed all of this, so I'm not going to talk about that over here. Because in some temperatures and in some cells, some modules, this is at the module level, so it's not going to exploit variation inside the chips. If you have more charge, you get faster sensing, faster restoration, and faster pre-charging. Yes, please. Because again, you have more charge, right? You can quickly restore things, and then you still have enough charge. So if you think about a large cell, if you restore, let's say, half of the charge over there, that's equivalent to the charge of a small cell. Does that make sense? Basically, you can restore little, and you can still get the same performance. Yeah. Uh-huh. Basically, the key is not restoring the whole thing. Does that make sense? Yes, if you restore everything, yes, then you're actually going to take time again. But again, also, it's not about largeness. It's also how fast you can do it, right? It's about the access transistor and the contact resistance as well. Make sense? Okay. 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 So essentially, yeah, basically this slide kind of covers that. If you're sensing, you can sense cells with extra charge faster. Again, this extra charge is, in a sense, covering for all of these different characteristics, faster cells, faster, I would say. As a result, you get lower sensing latency. If you're restoring, you don't need to fully restore cells with extra charge because they're kind of good enough or fast enough. You can quickly determine the value over there. You get lower restoration latency. And if you're pre-charging, then you don't need to fully pre-charge bit lines for cells with extra charge or strong cells. As a result, you get lower pre-charge latency. Yes. Mm-hmm. I think, again, not necessarily. Again, I would not think about this large or small, but fast or slow. So if a cell can be charged faster, you can reduce the write latency also. Now, this paper didn't do that, but some other paper that I'm going to briefly mention did that. Essentially, you need to profile the cells to figure out what you can do. Does that make sense? You still don't buy it? Okay. Okay. Okay, so we did a lot of characterization of this phenomena on real DRAM chips. You can this is actually one of the perhaps the biggest characterization study at the time on latency, and it used the soft MC infrastructure. And clearly, you know that this led to DRAM vendor, so you can do the studies on DRAM vendor today. So we verified all of this. So operating at low temperature, we've already discussed this. You get more charge, strong charge flow, faster sensing. And we see that you can actually reduce the activation latency by about 17% without getting any errors. Not bad, right? 17%. And this is average. So if you look at the paper, there's a large variation. There are some cells you can reduce it by 50%, some cells less so. Yes? Mm-hmm. With aging? That's a great question, basically. Mm-hmm. Mm-hmm. Exactly, yeah. We're going to talk about that later. Yeah. So this paper doesn't cover like dynamic effects, but later works will cover the dynamic effects, which are going to be important. And also they will bring out other insights as well. So how to do this profiling is important. You could do this statically, but then yes, over time, if the characteristics change, then you're in trouble. So you still may need to have some margin, right? But maybe different amounts of margin for different cells. Okay, but at low temperature, you're still not so bad. Okay, so again, if you want to reduce the restoration time, you don't need to fully restore charge at low temperature. And we see significant benefits over here again, reducing the read and write latencies. And again, we don't see any errors. This doesn't mean they may not happen if you actually run in the field 5 years. So that's always the difficulty with these studies. But I think this is the first study to show that you could actually do this in real DRAM chips in a let's say, in a reasonably reliable way, at least in the short term. I'm not going to show the pre-charge, but pre-charge essentially has similar results. So basically, the key idea is to optimize the DRAM timing parameters online. There are two components of this. This is what we envisioned at the time. Essentially, the DRAM manufacturer provides multiple sets of reliable timing parameters at different temperatures for each DIMM. This is not so easy, clearly, because you need to specify the timing parameter for each module. So it requires more testing, as you can see. But I don't think it's that bad also, because hopefully the second set at low temperature is more easily determinable than at high temperature conditions. And system monitors the DRAM temperature, which is already done today. Today, you have actually a lot of temperature monitors everywhere, not just the DRAM. And it uses the appropriate DRAM timing parameters that matches the temperature and the module. Okay. Yes. What do you mean exactly? Like inside, there are sensors in the DRAM modules, yes. Yes. They may not be everywhere in DRAM, but it gives an overall sense. So if you really want to do fine-grained temperature analysis, that may not be possible exactly today. Okay, so we also did a lot of measurement of DRAM temperature. It's actually hard to increase the temperature of DRAM unless you're stacking DRAM on top of your SoC. That's a place or processors, let's say. If you actually have DRAM stacked on top of your processors, then the heat goes to DRAM and the DRAM temperature increases. That's the case where this doesn't work as well. But if your DRAM is separate, like planar compared to your processors, it's very hard to increase the temperature of DRAM unless you start doing computation net. So keep those things in mind also, right? It's good to connect the topics. But basically, this is what we observed. We tried to increase the temperature a lot, and we were not able to do that easily. So previous works also showed that DRAM temperature is low in general cases. And other works actually try to maintain low DRAM temperature because high temperature is not necessarily good in general. Yes? Well, with 3D, you can do it. So we tried to do this with planar DRAM. Mm-hmm. So what we tried to do in this work is to increase the temperature as much as possible when DRAM is separate from the logic, far away, not in the same SoC, or not 3D stacked in some way. And writing programs that actually increase the temperature is not easy in that case, unless you externally control the temperature and increase the temperature. But if you're 3D stacked, yes, then your DRAM is directly exposed to the logic. Then you can increase the temperature much more easily. Yeah. Temperatures are probably much higher in those cases where you're 3D stacked, right? So probably, yes, the temperature like this, a technique like this is going to be less useful. But we're going to fix that problem in later works, hopefully. We're going to fix multiple problems. The problem you mentioned and the problem you mentioned, or the problem that we have collectively come up with. Okay, so basically, a DRAM operates at low temperature in the common case, as we have seen. So this is the summary of latency reduction, averaged across 115 DIMMs. This is almost 1,000 DRAM chips. So we see read latency and write latency reducing significantly, as you can see, 30 to 50%. And there's latency reduction for each timing parameter you can find. These are average, as I said, right? Averages. So your mileage varies clearly, depending on what kind of module you have, what kind of module you buy. You may be unlucky and you may have a module that's weak, right? You may be lucky and you may have a module that's pretty strong, and then you get better performance. This is one of the things that people don't like in general, right? You get not as, let's say, uniform performance across different things. So how do you price things becomes a question. So there's business-related issues over here also that we don't tackle clearly in science, but I think it may be good to think about. Okay, so we actually evaluated this on a real system. In some systems, you can change the timing parameters, as you can see over here, row pre-charge time, TRAS, etc., by programming the BIOS. And that's what we did over here. We programmed the BIOS with the timing parameters that we found based on our profiling. So we profiled the DIMMs using our infrastructure, figured out these timing parameters at low temperature is going to be reliable. And we programmed the BIOS to use those timing parameters. And we ran a bunch of applications. So these are real system results. First of all, we validated reliability. I think Dongkyok, my PhD student who did this work, ran the applications for more than a month, and he observed no errors. So that's one testing methodology, clearly, with the reduced timing parameters. And he also didn't observe that the temperature went higher than 55 degrees Celsius. So there's multiple validations. And these are the performance results that he observed in those applications with reduced timing parameters on the real system. And you can see that I think the average is actually larger than these workloads. These are a summary of some of the workloads. Yeah, 35 workloads we studied. And you can see that on especially memory-intensive workloads, you get significant performance improvements. That's about 6.7% performance improvement. And this sounds low, but it's not really low, right? This is something that you gain without doing almost anything. Right? This is real performance results. It's not simulated either. So simulations, you may argue, and we're going to talk about simulations later. It may have errors, but this is real results. You get the results of the application reliably. And you can see that some random access application, GUPS, that's a random access application, giga updates per second, it actually benefits higher than many others. Because random access is not good for latency, clearly. You open and close, you get bank conflicts, and you open and close the row buffer. And reducing that latency improves the performance of that application more than it does others. Okay, so on average, it's about 5%. Of course, with memory non-intensive workloads, you don't get a lot, but that's expected. If you're not accessing memory latency is not your bottleneck. Okay, so the performance improvements, of course, increase if you have multiple cores accessing memory. And in this case, on intensive workloads, we see about 14% performance improvement. And we're going to talk more about that later on when we talk about quality of service, multiple, essentially designing memory controllers to handle multiple threads, etc. But in general, as the load on the memory system increases, the importance of both memory bandwidth and latency increases. And again, these are real results from real systems. Okay, so it's always, if it's possible to do, it's good to test your results on a real system, but it's not always possible to do, right? All of the other techniques that we have seen in the last lecture, we cannot test on a real system because these are ideas that change the hardware significantly. Even though here we kind of propose some changes to the hardware, you can evaluate, let's say, bare bones version of it in existing systems, right? That's not exactly what we envision. We don't say basically these latencies should be set at the BIOS. So there's no dynamic component to this. We basically say we set the latency parameters assuming that we're not going to exceed this temperature. And we don't see exceeding that temperature, so we can actually do the study. Okay. So we also, based on circuit level evaluations, we also see that reducing the latency to the parameters that we have found reduces power consumption as well. Take all of these numbers with a grain of salt. Power consumption is much harder to evaluate in general. And we have much better power models right now in 2024 compared to 2015, etc. But essentially, you can reduce power consumption because you're really reducing the activation times and the sensing times and the restoration times. I think this one is specifically for activation. That's why it's relatively low over here. But this is what I meant earlier when I said reducing latency is good for many things. It's not just for performance, but it's for energy as well. You keep the circuits active for shorter amounts of time. Make sense? Okay. Okay, so let's talk about advantages and disadvantages a little bit. I think you kind of found some disadvantages. So essentially, this is a simple mechanism. So that's one advantage. Clearly, it works even if we don't do much. And this is actually some things what people who do high performance gaming do, right? They already try to reduce these latencies. In fact, after we published a bunch of these papers, I got a bunch of emails from gamers. And these gamers said, we really like what you have published because that gives us a methodology to really reduce our latency so that we can get higher performance. These guys are really at the cutting edge in the end. They really, but what we have provided is really a methodology to do that reliably for them. So there are a bunch of really long emails that I have in my mailbox. And please feel free to send them. I'm happy to look at your emails, but maybe not necessarily respond to them. It's good to see that our work is having impact on not just scientific community, but people who really care about getting high performance, right? And there are also, of course, companies who use our work and they don't say anything in there. That's kind of a shame on them. Yeah. Okay. And it leads to significant system performance and energy benefits. That's clearly there. And I can verify that with emails from people who really care about at least the performance aspect of it. Maybe they don't care about energy aspect of it as much. And you get benefits at benefits are higher at low temperature. Which means that benefits are not high at high temperature, as you can see. We can try to fix that in some way. It's low cost and low complexity. That's true, I think. Now, disadvantage is you need higher testing costs. Basically, you need to determine reliable operating latencies for different temperatures and different dips. So there's this testing cost that you have. And there's also the thing that you mentioned that I didn't put over here, but in a later work, we're going to cover. How do you actually deal with long-term effects, right? So doing this profiling once is not enough. we kind of say you should probably do this profiling multiple times over time, but it's not clear how often. So that's a good question, basically. And also, how do you do the profiling is another question. Right? It's kind of similar to retention time profiling that we've discussed. We introduced ECC, for example, for that retention time profiling. I think we're going to introduce that also here. So without ECC, it's very difficult to do profiling of either retention times or latencies in memory. Any other disadvantages you can think of? This is a work that's almost 10 years old now, so there are a lot of disadvantages that are uncovered. But it's still the first work that actually pushed this notion that you can actually reduce latencies by reducing the timing margins. Okay, well, I said might not be that difficult for low temperatures, but we're going to talk more. Okay, that's the paper. So as I said, this paper looks at the module as a whole. The type of variation it exploits is really across temperature levels and across modules. There's also another variation. Well, I guess kind of said this, which is within a chip. I asked this question over here, but I kind of answered this, right? There's always a variation within, always some sort of variation within the chip, across different parts of a chip. And that's what we're going to try to explore in the next one. I'm not going to cover this in more detail, but we're going to look at different types of variation within a chip. So we actually expand our infrastructure to do more chips, more testing, and more studies. Let me take a look at, this is the TRCD, which is activation latency variation. So this is the standard at the time, 13.1 nanoseconds. And we're going to reduce it all the way to 2.5. And we're going to look at the bit error rate that we observe from different chips. So essentially, I don't remember the temperature level over here, but it's not high temperature. It's maybe 50 degrees Celsius. So you can read the paper for more detail. Yes. Yes, really burning question. Yeah. So that's a great question. Ask Giray. Or ask Altaberk or Ismail. I don't know where they're. Ismail is absent, so you can ask Ismail. Find him. I don't see him, at least over here. But basically, it's possible. Yes. So these combined effects need to be examined more rigorously. And these are some things that we're doing right now. But that's a very good question. Maybe you can investigate that in more detail, in more depth. Do you have an answer? Okay, there you go. Not immediately. Yeah. Yeah, exactly. That's the beauty of presenting these results, right? You come up with questions that no one has completely rigorously answered. I have a small answer, but I'm not going to blurt it out over here. We can discuss it separately. Okay, so basically at low temperatures, there are no activation errors that we see across all of these chips, across many rounds. Rounds means rounds of testing. You test many, many times, basically, to see what's happening. Because you may get some random errors in one testing, but in the remaining 7,000 testing, maybe you don't get errors, right? Okay, and this is the bit error rate distribution that you see as you reduce the latency. So this is 7.5, and you can see that this is the minimum bit error rate that you see, and this is the maximum bit error rate that you see, and these are the quartiles across different chips. Essentially, in this work, we verify that you have different characteristics across different DIMMs. There are some DIMMs that have very few errors, even when the latency is aggressively reduced to 7.5. And there are some DIMMs that have many errors. If you keep reducing the latency, of course, all DIMMs stop working, let's say. So at 2.5 nanoseconds, almost all of the DIMMs have a lot of errors. A bit error rate of 10 to the 0 is essentially all cells are erroneous, right? Okay, but this is what we study. This is kind of also validates AL-DRAM's results. But where do the errors happen? So this is also what we try to study. So this here you see, I think, one bank, 16,000 rows, and this is 128 columns, basically different cache lines. You can see this as the picture of a bank, and we're looking at the distribution of errors at when you reduce the activation latency to 7.5 nanoseconds. And you can see that only a very small fraction of the cells have errors. Most of it is white, meaning that your error rate is 0. So this is the color scheme corresponds to the probability of a cache line having more than or at least 1 bit error. White means 0, black means 27%, I think, in this case. So there are some areas that are actually pretty bad. in this particular case, right? This is just one DIM. So essentially, our conclusion here is that activation errors are concentrated at certain columns of cells. So if you can somehow figure this out, maybe you can develop techniques to actually overcome this, right? I'm not going to go into a lot of those techniques. You can potentially protect those things, assuming you have a small number of those columns, which is not that small in our experience. But the solution that we propose in this case makes the memory controller a little bit more intelligent. Essentially, we call it flexible latency DRAM. It's a bit expensive in the memory control level, but the idea is that it's a software transparent design that reduces latency. We divide the memory into regions of different latencies, and the memory controller uses lower latency for regions that don't have slow cells, and it uses higher latency for all of the regions. For example, if you're accessing a cache block that's here, you can access it faster. Right? If you're accessing a cache block that's here, you need to access it slower. Makes sense, right? This requires you to keep track of which cache blocks can be accessed faster or slower on a per DIM basis, per module basis, which is expensive. Make sense? Not easy, but I think it's good to do these studies to understand the limits. And that's the idea. For the paper, for more detail, you can read the paper. But let's take a look at potential benefits you get if you can actually do this. This is, again, based on real chip results. We look at two parameters over here, activation and pre-charge latencies. And we actually have profiles of 3 real DIMs. So if you know nothing about the DIM, you always access it with 13 nanosecond latency parameters, right? In this particular DIM D1, you have 12% of the cells that could be accessed with 7.5 nanoseconds, and the remaining can be accessed with 10 nanoseconds. In this particular D3, DIM 3, you're much more lucky, let's say. 99% of the cache lines can be accessed with 7.5 nanoseconds, and only 1% at 10 nanoseconds. We don't access anything at 13 nanoseconds because 13 nanoseconds is too much, at least at this temperature level. Make sense? So with these 3 profiles, and then there's an upper bound, of course, you access everything at 7.5 nanoseconds, right? That's ideal, but we cannot achieve that reliably. And according to our simulations, these are the results that we get. This is the baseline, and I don't know why this bar is not the same. It's kind of annoying. It's not at the top of that blue, but fine. That's at 1.0 level. And if you have more cells that can be accessed faster, clearly you get higher performance benefits. So basically, these are the benefits that you get as the fraction of cells increases based on what we've measured. And you can see that if the fraction of cells is 99% that could be accessed faster, it's almost as good as an ideal upper bound, as expected also, right? So this paper shows the potential of exploiting within chip or within module variation. And you can see that the potential is relatively large based on our measurements. Of course, building the memory controller to actually make this work is the harder part, I think. And this is, I think, still a somewhat open problem, I think. We don't have extremely good way of specifying what cells can be accessed with what latencies, because we don't have that sort of luxury in a DRAM controller today, right? We're going to talk about flash controllers, for example. You have a remapping table in a flash controller, and that remapping table can store a lot of metadata related to each page. We don't have that luxury in DRAM because it's expensive in the memory controller. But if we actually change DRAM and start thinking about it in different ways, perhaps we can add this metadata on a per region basis and access cells at different latencies. So it's good to think about this for the future. The same problem, a similar problem exists in what Giray presented a few lectures ago on spatial variation across different rows, right? That's relatively hard to do today because you don't have storage or metadata storage in your memory controller to store what is the RowHammer vulnerability of each row, right? If you have a better or more intelligent or more expensive memory controller, you could store that. And that metadata storage could be used for storing latency information also potentially, right? Assuming it's at the same ground-level. But in general, the storing metadata with different memory locations is a not completely solved problem. And we may talk about that later again. Does that sound interesting? Yeah. Okay, and there could be other benefits of this metadata as well. Okay, but the takeaway is that if you actually are able to do this, you can improve latency even more. Okay, now let's talk about advantages. I think I've already kind of covered the advantages. Latency is reduced even more significantly by exploiting this intra-chip variation. But now there's even higher testing cost and more complicated controller, as we have discussed. And this is a paper that actually uncovers it. It has a lot more data than what I just described. You can take a look at it. So there's another work that I'm not going to talk about that puts it all together. It's very nice, but we don't really have time to cover everything. I'd recommend you take a look at it. It's a relatively short paper. It also actually shows you a way of reducing the write latencies even more than we have discussed. But I'm going to keep that as a teaser and not discuss. There are some backup slides. If you're interested, you can look at the backup slides without reading the paper. But I like this paper, but I don't have time. And actually, it has a lot of interesting analysis, like the spatial distribution of failures. So by actually doing latency profiling, you can do a lot of reverse engineering of DRAM as well, because the latency profile gives you an idea of the structure of DRAM, because in different subarrays, different columns fail, for example. Okay. Now, after this, we asked even more questions. Basically, there's spatial latency variation within a chip. What are the reasons for it? Clearly, weak columns is one reason, but we're going to talk about some other reason over here as well, because there's some architectural variation also that we may not be exploiting. So we call this design-induced variation. And I like this concept because that's actually very architectural. If you look at a subarray in DRAM, you have the word line drivers that activate the word lines, and they have sense amplifiers that sense the bit lines. Right? It's a two-dimensional structure. So assume that this is the structure and ignore all of the other, like let's say, sensing circuitry, etc. Ideally, as you go farther from the sense amplifier, cells should be slower. So there should be some, because there's a longer bit line, longer sensing latency, right? If you're closer to the sense amplifier, this should be sensed faster, right? Because your charge perturbation is quickly sensed over here because of the distance, lower distance. So there's a crossover variation that's dependent on the distance from the sense amplifier. Slower cells are up here, faster cells are down here. And then there's a cross-column variation architecturally. If you're closer to the word line driver, you should be accessed faster, right? Because word line driver drives that part of the line earlier, let's say. Whereas if you're farther, you should be accessed slower. So this is theory, of course, right? Based on circuit theory, this is what you would expect. We're going to validate it in real DRAM chips, and we did in this work. So there's an inherently fast region in a DRAM chip, there should be. And then there's an inherently slow region, not just chip, but it also in the subarray. So we're looking at a subarray level over here. So if you can somehow identify this inherently slow region, you should be able to set the latencies based on the latencies of that, or reliable operation latencies of that slow region, right? That's the idea. Don't profile everything. Don't test every single cell over here. Test only the slow region, assuming you know where it is. If you can figure it out by testing, of course, initially, or the DRAM manufacturer tells you exactly where it is, and then you test only a few cells to determine the latencies, reliable operation latencies. That's the idea over here. Well, one of the ideas. Okay, basically there's systematic variation of cell access times that's caused by the physical organization. So we propose this online profiling that I just alluded to. We call it design-induced variation aware. There's an inherently slow region. Identify that and profile only those regions to determine the minimum latency to access a subarray with. You could do this at the subarray level. And this hopefully gives you a low-cost latency optimization. And this also reduces the profiling cost, because if you want to check whether your profile changes dynamically, you don't test the entire chip, right? You just test that inherently slow region. Sounds good. Sounds great, except it's not complete. Meaning there are slow cells that are slow for other reasons as well. So it's not just about architectural variation. Everything so far you've learned in this course also says there's process variation as well. So what do you do about them? Unfortunately, those are the thorns in the rose. So if you don't do anything about them, your hand will bleed because you're going to hold that tightly, right? Okay, basically, these slow cells you need to deal with somehow. And the idea in this work is to really distinguish between them and distinguish between their profiling, let's say. So inherently slow region happens because there's design-induced variation, and you get localized errors. Slow cells happen because there's process variation. In this case, you get somewhat random errors. Not always random, because some columns may be actually weaker. So there could be actually more than random errors. But assume for now, you deal with those columns in some way. You can actually deal with the columns more easily. But if it's truly random, meaning not an entire column goes away, then you can handle those with error correcting codes. This is really the use case for error correcting codes, right? These are errors that you don't know why it's happening. These are random errors, and you can correct them with error correcting codes. And this is what the paper proposes, basically. Do online profiling to reduce latency as much as possible, and reduce latency in such a way that error correcting codes protect the other cells that fail due to process variation. So that's the idea. And it's a combination of error correcting codes and online profiling. And this is, again, to reliably reduce the DRAM latency. In a sense, this makes AL-DRAM work. So this is the work that makes adaptive latency DRAM really work, in my opinion. You can do this profiling continuously, dynamically. So aging effects, for example, you can figure out as you keep profiling online, because the profiling cost is low. And you have a fallback, meaning if you get errors, error correcting codes will correct them. And I don't think there's a better way today to do online profiling. You have to have error correcting codes. We've seen that in the Avatar paper, for example, right? Or the Reaper paper. You have to have error correcting codes to do any kind of online profiling. Static profiling is not enough for reasons we've discussed. You need to do online profiling. And if you want to do online profiling, it's very difficult to do it without error correcting codes. If you come up with some better way, let me know. Again, there's potential research here. So if you do that, let's take a look at what benefits we get. So this is, again, AL-DRAM tested with newer DRAM chips that we test over here. These are reduction in read latencies. And we replicated the AL-DRAM results. You can actually reduce the latencies even more than AL-DRAM does. And you're less sensitive to temperature at this point. Even at high temperature, you can reduce the latencies because you have these error correcting codes that can reduce things, that can correct things. There's also something else in the paper that takes advantage of the locality of errors to do better error correction that I'm not going to talk about. But if you take advantage of that, you can actually become even more reliable, plus reduce the latencies even more. And write latencies are also similar. So basically, as you can see, this way you can do better than AL-DRAM while being more reliable, which is interesting, right? So we solved all of the problems with AL-DRAM while making things more reliable, except it came at a cost. Okay. So I think the big advantage of this is, that's why there's a plus over here. You can now automatically find the lowest reliable operating latency at system runtime. Meaning, maybe you don't need to do as much testing at the production time, right? Not as much rigorous testing. Maybe you start slow, and over time you figure out how to go fast, right? How to access cells faster. So I think this sort of mechanism is actually very useful. It's more dynamic latency optimization. And reduces latency even more than prior methods, but of course with the ECC. And has high temperatures as well, again, relying on ECC. And also this online profiling helps. But of course, this has more disadvantages potentially. It requires knowledge of inherently slow regions, which requires in turn reverse engineering or information supplied by the DRAM manufacturers. It requires error correcting codes, of course, but I don't think you can get away with that, as we have discussed. It imposes overhead during runtime profiling. That's also true, but hopefully that's relatively small because you have a good knowledge of the inherently slow regions. And now you have more complicated memory controlling. Now it's capable of profiling, capable of correcting, capable of essentially making sure everything works. On top of that, it needs to actually, of course, decide what area can be accessed with low latency and high latency. So that part still remains, right? So you need to still have a mapping of a physical address and how fast you can access it with. And this is the paper. It was published some years ago. It has a lot of data, a lot more data also. And also this, I think this paper also has nice data on reverse engineering the DRAM structure, understanding. It didn't go all the way to reverse engineering at the math level, but the data, the latency data that it provides can be enhanced to actually reverse engineer things at the math level as well. But you have to look at the paper for understanding what that means. Any questions? Okay, if there are no questions, this is probably a good time to take a break. because I'm going to switch gears a little bit. So let's take a break for 15 minutes until 14:23, and then we'll be back. you can have more years of research, not PhD. Yeah. Exactly. Okay. So it's just about that. Okay. Okay, let's continue. Let's see if no stragglers visible. Okay, so we have looked at changing the one-size-fits-all approach to latency specification for the top three: temperatures, different DRAM chips, different parts of a DRAM chip. I'm going to defer the supply voltage levels to later today. I'm going to talk about application data, which we have briefly talked about in the past, but I'm going to remind you. Essentially, you can also take advantage of the characteristics of the application data to change the latency, right? Today, we don't normally do that. Whenever you access DRAM, everything is equal latency. But if you know your application, you can design the latency characteristics to meet the characteristics of your application's potential error tolerance, for example. And this is what we did with this Eden work. Essentially, we looked at deep neural networks. It's especially for large networks, the evaluation is very DRAM intensive, and we've seen that in some other works in the past. But some data and layers in deep neural networks are very tolerant to errors, and some of them are not. And the idea is to reduce DRAM latency and also voltage aggressively based on the error tolerance of different data and different layers in the network. And the goal is to still achieve a user-specified accuracy target. And to be able to do that, you can actually change the training of the neural network to be aware of the errors that you're getting when you reduce the latencies. So that's the idea over here. I will not go into a lot of detail because it's a full system that discusses it. It's actually a nice idea, I think. And this is an example of data-aware management of DRAM latency and voltage for accelerating or making more efficient deep neural network inference. So this is an example. This is weights and input feature maps of different layers of the ResNet 50 network. And on the x-axis, you have the maximum tolerable bit error rate for different weights and input feature maps. And this is the idea, basically. There are some DNN layers that are actually very tolerant to errors. You can have, and this is determined based on, of course, some testing, right? You inject errors and you figure out that even if you have a 10% bit error rate, you still get a good accuracy or good enough accuracy. And then you can train based on those errors and you can make your accuracy even better. So that's the idea over here. Figure out which parts of your data are actually more tolerant. In this case, these are more tolerant. But these areas are not as tolerant as you can see. To achieve an accuracy target, the maximum error rate that you should have is about 2%. But if you know this profile of all of your data and input feature maps and weights, then you can basically map more error tolerant data to DRAM partitions with lower voltage and latency. Hopefully that makes sense. Or put another way, reduce DRAM voltage and latency to satisfy the error rate that is needed for the data that's mapped to that partition in the DRAM. So in this case, for example, you can have 4 partitions with different error rates. One partition can be designed such that latencies and voltage is reduced such that you don't get more than 2% bit error rate. Another partition, you don't get more than 5% bit error rate. Another partition, you don't get more than 6%. Another partition, you don't get more than 8%. Make sense? This is the kind of optimization you can do if you actually know your application and its error tolerance. Of course, you should be able to modify your DRAM to satisfy these error rates as well. Okay, this is the overview. Essentially, this is the goal. We want to have like approximate or error-prone DRAM to accelerate and make DNN inference efficient, but while keeping the accuracy. So to be able to do this, you really need to have an iterative process, meaning you need to characterize your DRAM error rates, figure out the error models, etc. And the paper talks about that. You need to characterize your deep neural network, and you need to match the deep neural network parts to the DRAM with different error rates, and then you will get some sort of accuracy, right? And if that accuracy is not enough, you keep retraining based on the errors that you see, so that you actually get better error tolerance when you're executing. So there's an error-aware retraining that is described in this paper, but other people also do this basically. If you get more errors, you retrain the network so that you can tolerate those errors. And you can read the paper for more information and also references to other papers. But if you keep doing that, you can preserve your accuracy. And I'm not going to go through this in detail. Yes? Mm-hmm. Yeah. Yeah. How can this be applied instead of doing static? Well, statically you can do it, right? So for example, if you have a machine learning accelerator, a lot of things are done statically over there. You don't have an operating system in between the application and the hardware. So over there, I think it's relatively easy. Yes, if you need to do it in a general purpose system, you need to somehow drill down. And this is, I agree with you. This is synergistic with everything we talked about, right? How do you expose more information from the bottom to the OS? And how does the application communicate that information through the OS to the hardware? So this is static right now, yes, exactly. So, or this assumes a way of doing this through the OS that's actually, I mean, one way of doing this is, for example, the OS can give this memory directly to the application, right? If that's given, then you don't need to go through any of that virtual memory mechanisms. Does that make sense? If you want to go through virtual memory, then yeah, you need to add more mechanisms. Okay, good question. Okay, so basically the paper evaluates things using those 4 DRAM partitions, and these are the results that we see. Essentially, you get significant DRAM energy reduction while maintaining accuracy within 1%, assuming you are fine with that accuracy loss. And in CPUs, you also get speed up, and some workloads actually achieve higher speed ups because some of the portions are actually more latency sensitive. And you get close to ideal speed up, basically, by reducing the TRCD to 0. Okay, the paper has more evaluation that I'm not going to go into, for example, on GPUs or machine learning accelerators of different kinds, like Google TPU, for example. You get about 30% average energy reduction and performance improvement. And again, I wanted to give this to you because it's another way of reducing latency, right? Assuming you can actually modulate the latency at the device level, and then you understand your application, you can match the characteristic of your application to the latency. Okay, and there's more talks. I think in the past, actually, we have had cutting-edge research talks on this topic. But probably we're not going to cover this this time. Maybe we'll cover something else. Okay, so this is similar to what we have discussed, heterogeneous reliability memory. I'm going to just remind you, I'm not going to talk about this again, but somehow identifying the error tolerance of your data enables a lot of opportunities, I think. And again, this goes back to this question, how can you do this efficiently? We've covered this, so I'm not going to talk about that. But basically, you will need to somehow characterize and classify the memory error tolerance. You could apply this technique to actually even more broadly, right? It doesn't need to be memory. It could be logic error tolerance. But somehow you need to identify your application's vulnerability, different portions of your application, as a continuum. And based on the vulnerability or tolerance levels, you map the application to different parts of your memory with different characteristics. That's the basic idea. And I think this is a very general idea. It can enable a lot of optimization. Maybe there are more ideas to be explored over here. I'm putting it out over here, even though we covered this in an earlier lecture. But this is, all of these are examples of heterogeneous reliability memory mechanisms, in my opinion. Eden is an example of this work generalized in a sense. Okay. Any questions? Thoughts? Yes. Yeah. Mm-hmm. Like control at the hardware level? Like potentially, yes. Actually, I mean, for example, you can change the voltage level. You can change the latency levels today, let's say. But maybe you can actually have even more fine-grained control. Maybe you put more margins to the latencies. Yeah. Yeah. Yeah, but you need to test, you need to understand that probability function, right? There needs to be a modeling or profiling that needs to be done to understand that function. Yes. But there are controls in place, and there may be other controls that could be put, right? For example, one other control could be changing the strength of the error correcting codes. Assuming you have that possibility, you could change the strength of your error correcting codes, right? So in this paper, if you remember, we also said, yeah, I guess basically changing level of ECC or type of ECC is what you use, parity or no ECC or some stronger ECC. I guess testing doesn't really allow you to control because it's static or pre-production or maybe post-production way of doing it, but yeah. But there are controls. The difficulty is, I think, for identifying that function. Maybe you have some ideas to build on that, so that's good. Okay, now I'm going to get back to voltage levels. Even though in this work we actually exploited the voltage levels, now let's take a look at this voltage latency reliability relationship. So things get more complicated as you add more and more things, right? We were talking about latency reliability. Now we're going to add voltage, and that's going to make this even more complicated, I think. But we can still understand things by testing. And that's what we wanted to do, basically, because one of the reasons is we wanted to save energy as well. And this is a paper that actually characterized in detail. Later, Giray did work on understanding the word line voltage and its effect on RowHammer, for example. So there's, I think, more to be understood if you build infrastructure to do voltage studies. And you can see that Giray actually did a lot of infrastructure work too for this paper. Okay, so one of the goals that we had in this work was to actually reduce the power of DRAM, reduce the energy consumption by modulating voltage. And we've already discussed that power is a big, DRAM is a big power consumer in existing systems. Then there are many questions over here, right? How does reducing voltage affect the errors or reliability? How does reducing voltage affect DRAM latency, meaning reliable operating latency? And assuming we understand this, how do you design a new DRAM energy reduction mechanism? So essentially, you can control the supply voltage that goes into a module, and you can adjust the supply voltage to every chip on the same module. And for this, we built an infrastructure with a voltage controller. You can ask Giray about that a lot. He built multiple of these, right? And clearly, DRAM vendor has a version of this that supports it. So I'm going to mention DRAM vendor again. And these are the things that we tested at the time. Essentially, 124 low voltage chips. And I think essentially we look at the nominal voltage on these chips is lower than regular DDR3 because they're supposed to be low voltage. So 1.35 volts. And these are the characteristics, as you can see. And essentially, we also look at how can we reduce the voltage. So we can actually reduce the voltage by about 26%, which is substantial, but it's not huge, let's say. You can go down to 1 volt. If you could go down lower, that's actually good, but you start getting a lot of errors, as we will see. So this is an example study that you could do by changing the voltage. So this is our nominal voltage. So everything should operate without errors over here. And we're depicting the fraction of cache lines with errors over here as percentage and different vendors over here. So this is what happens if you actually reduce voltage from right to left. So you can see that there's some margin over here. For vendor C, the margin is very low, meaning at this point, you get a lot of errors very quickly. That's almost 10%, right? But then for some other vendors, the margin is pretty high. So you can exploit some margin, as you can see. Let me see. So clearly, this part over here is the minimum voltage without any errors that are seen. And you can go down to 1.15 volts, which is promising. So there's some margin in the voltage also, as you can see, right? For the same reasons that you have margin latency. So basically, reducing voltage below Vmin causes an increasing number of errors, which is as expected. Because if you reduce voltage, you don't have enough time to actually, the circuits operate much more slowly, and you don't necessarily have if you keep the same latency parameter, you don't get the data correct. But at some point, if you reduce the voltage too much, the circuit may not operate as well, right? You may not be able to switch enough. So we wanted to understand these different characteristics. So we also built like circuit models, spice models essentially, to really guess what could happen with supply voltage as you change the latency also. So this is supply voltage on the x-axis again, nominal voltage here, and this is latency. Latency that you need, the reliable operation latency, so that you can actually you don't get bit errors. This is what we expect based on our circuit model. So this basically shows that at lower voltage, you should increase the latencies so that you don't get errors. That makes sense, right? You need to give circuits more time to stabilize, basically. So this is theory again. Theory meaning simulation. And this is, it's always good to try to test whether the simulation has some matching behavior in real chips. And that's what we did essentially. So I'm going to show you the matching, let's say, real data. And it kind of looks like that, right? So we expect a curve that looks like this. As you reduce the voltage, latency should increase. This essentially shows the same thing. On the x-axis, we change the supply voltage. On the y-axis, we change the latency. And this is the measured minimum reliable activation latency. And I'm going to explain what these circles are. Essentially, this circle means 100% of modules can operate reliably at this voltage level with this latency, XY points basically. So at nominal voltage level, 100% of modules can operate reliably with a latency of 10 nanoseconds, a TRCD, I think. And clearly, I think this is one vendor, I don't remember, but this is one of the vendors that have enough margin in the previous picture, earlier picture. So you can see that there's huge margin. So 100% of the modules can operate reliably until you get to a voltage, supply voltage level of 1.10, 1.1. At that point, some modules need higher latency to operate. So you increase the latency to 12.5. The reason we go by 2.5 nanoseconds is because that's the minimum granularity at which we can change the latency in our FPGA infrastructure. But still, you can operate. You can have 100% reliability, and 90% of the modules don't need to increase latency, as you can see, right? Now, as you keep reducing the voltage even further, you start losing some modules. 50% of them still operate reliably over here. 40% require higher latency, and 10% are dead, meaning there was no way we could operate them reliably, even if you increase the latencies even more. So something happened in the circuitry that we cannot fix, basically. You need higher voltage for those modules, for example. And then as you keep pushing the voltage lower, you lose more modules, as you can see over here. And at some point, you lose all the modules. But this curve, measured in real devices, looks quite similar to this curve that we expect in, well, we expect it based on simulations, right? And this is nice. Of course, the exact numbers may not be exact because we don't have the exact parameters that is used in real DRAM devices, but the shape of the curve validates what we have expected. Okay, but basically the takeaway is that if you want to operate at aggressively low voltages, one option is to have longer latency to access data. There could be other options, right? And we have, GI actually looked at that a lot and he couldn't find out anything really perfect in that case, but you could, for example, add a lot of ECC, etc., for example, where you can talk to GI about that. Okay, so that's one observation. There's another observation, which is spatial locality. So errors actually have a lot of spatial locality. It turns out some banks get a lot more errors, and some banks don't get errors if you aggressively reduce voltage. This could be due to some like poor power supply that goes into each bank, potentially, right? Or difference in power supply that goes into each bank. But if you know this information, you can potentially map your data intelligently as well, right? Of course, this will depend on each module. So again, you need to have this intelligent memory controller that tells you which module has what characteristics. And I think that sort of metadata would be very useful for many different purposes in the end. It's actually good for your purposes also, right? Yeah, like we've discussed. In the end, it boils down to how do I store metadata that describes the heterogeneity that is actually present in the underlying memory and hardware. Okay, so this paper, I'm not going to go through the mechanism in detail, but basically, assuming you can quantify all this, which we did, the idea of the mechanism is to select the minimum DRAM voltage without violating a target performance loss. So there's a target performance loss supplied by a user. User says, I cannot tolerate more than 5% performance loss, save as much energy as possible, right? That's the idea. If that's the case, then this paper provides a mechanism to predict performance loss at low DRAM voltage operation points. And the performance loss comes from increasing the latency at low voltage operation points, right? So this paper develops a linear regression model that I'm not going to go into. I don't think this is the best model. There could be other models. People can use other machine learning techniques than linear regression, maybe neural networks, etc., maybe something else. But essentially, this is a model that takes as input the characteristics of the application and the voltage and gives you a predicted performance loss. I think we can do much better today than 7 years ago. But we still did not bad in this case. And in the end, basically, you decide a minimum voltage. If the minimum, and then you decide essentially what kind of voltage to use to keep the performance loss under check, under control compared to the target. Okay, so if you do that, essentially you get significant benefits. So this is Voltron, let's say. Wait a second, I'm trying to read this. So at low memory intensity workloads, these are the energy savings that we have in the system. Low memory intensity means you're not exercising memory a lot. That means that the savings are expected to be lower. But at high memory intensity workloads, you actually save a lot more energy. So you can reduce the voltage and save more energy because at high intensity, you're exercising memory a lot. And as a result, you can reduce the energy more. And the savings are significant. This is our own prior work, actually. It's actually a nice prior work that I'm not going to talk about. This is work we did with Intel almost 14 years ago, as you can see. And the idea over here was to change the voltage level of the bus, frequency and voltage level of the bus, not necessarily the DRAM circuitry in turn. And the way we did it was if you actually are not using the bus, reduce the frequency and reduce the voltage. That's why it's called MEMDVFS, right? It's a memory dynamic voltage and frequency scaling. And this is beneficial at low memory intensities. But if your memory bus is always used, then this is kind of useless, right? You don't want to change the memory dynamic voltage and frequency scaling. But in this work, actually, we built a full FPGA-based infrastructure to test this together with Intel. So in that sense, I think the work actually was very interesting. Okay, so this is the performance. This is the energy savings. But then there's also the performance target. So according to our model, we determine the voltage. And we see that in practice, we don't actually violate the performance target as well. So basically, the performance loss, we get some performance loss, but the performance loss is much lower than the target that is provided by the user. So there could be better mechanisms, of course, to predict performance. And hopefully they could make a better trade-off, right? Maybe you could save more energy while losing more performance, who knows? This is not ideal, of course. Ideally, you would like to improve performance and improve energy at the same time. But I think here the energy savings are much larger than the performance losses. And again, if you have performance slack, this sort of optimization is good to do. Thoughts? Okay, I think this gives you an example of more complex optimization space. And I believe going forward, using machine learning techniques to understand this or predict this optimization space is going to be interesting. Okay, so advantages, I think it's clear that now you can trade off between latency and voltage to improve energy or performance. We did not look at performance improvement in this case, but you could potentially say, well, I'm going to increase voltage to lower latencies, right? So that's another possibility over here. But now you expend more energy, of course. But we did not look at that. Then you can exploit the high voltage margin present in DRAM. Again, disadvantages, you need higher testing costs. That's true for any mechanism that we've discussed today, I think. Because this requires finding the reliable operating voltage for each chip, potentially for each bank, if you want to exploit the variation inside each chip. Again, more complicated memory controller. It's not news because all of the mechanisms that we've discussed requires more complicated memory controller. And Giray has delivered lectures on this topic, so if you're interested, you can watch him or catch him. Okay, any questions? No? Are these interesting? Boring? What's interesting is what comes next, I think. That's the thing we don't know. I think there should be more optimization to be done. Okay, so now I'm going to switch gears even more and talk about reducing memory latency to support security primitives. This is an area that we have also stumbled on when we're actually modulating latencies. It's kind of a more serendipitous area, meaning we were not really targeting to do security primitives. Our goal was to always improve performance with reducing latency. But we also found out that you could actually do interesting things with DRAM that people have not done before. So I'm going to talk about several things. I'm not going to cover probably everything over here. There's a lot here. But as we have discussed in the memory-centric computing lectures, you can generate true random numbers by violating the latencies. You can actually evaluate physical unclonable functions, which I'm going to start with. That's the first work that we have done. And also, you can quickly destroy in-memory data. We have seen this with row clone, for example, or multi-row copyright. But we'll see another mechanism, at least at a very high level, that could actually quickly destroy in-memory data, which could be very useful, especially if your memory is compromised. If someone stole your memory, and if they want to read what's in there, if they want to do a cold boot attack on your memory, for example, if they power it up, it'd be nice if your memory completely destroys itself, right? These are the cases where it could be useful. And I've done enough work on SSDs and memories that there will be people who would like your data, for sure. Okay, so let's take a look at the physical unclonable functions. I think this is, I mentioned this in the memory-centric computing lecture, but I'm going to go through this a little bit more detail over here. But basically, what is a physical unclonable function? It's essentially a function that's unique to the device. That's why it's unclonable. If you have this device, if you apply this function, the result will be unique to that device. Makes sense, right? You could call this a signature of the device. A PUF or physical unclonable function is a fancy term. So you could actually add circuitry to the device to create this physical unclonable function. Or you could exploit the characteristics of the device to create this physical unclonable function. For example, you could add an oscillator circuitry, and that could actually give the identity of the device, right? And of course, the characteristics of this physical unclonable function, the security characteristics are also important. If someone can quickly figure out the device, let's say, to mimic the identity of your device, maybe your physical unclonable function is not good, right? So basically, we're going to look at the second approach, which is using the characteristics of the device to create this physical unclonable function. And I think I've already given you the key idea, maybe without a picture at the time. If you actually reduce the latency of DRAM, cells fail at different cells fail at different latencies. And at a given latency parameter, some cells always fail. And if you choose the latency parameter carefully, these cells that fail form a unique signature of the device. So in this DRAM chip, cells 153 fail, for example. In this other DRAM chip, cells 5000, 5005, 5007 fail. And that's really unique across different DRAM chips. And that's the idea over here, basically. Reduce the latency. Okay, but I will give you the motivation without going into a lot of detail over here. And I'm at slide 89 over 45. That's nice. That's why we should not have slide numbers, because this is a copy paste, as you can see. So why do we have physical unclonable functions? Essentially, we want to make sure that a system's components are not compromised. It's a function that you evaluate on a device to generate a signature that's unique to the device, as I mentioned. And the unique signature is a PUF response. And it's often used in a challenge response protocol. It's called CRP. Essentially, you want to do attestation of the device. You want to basically, you're talking to the device, and you want to make sure that the device is not compromised, meaning someone didn't, for example, change the device to be something else. In this particular case, we're going to look at the DRAM. Someone didn't change the DRAM to be something else. because if your DRAM is compromised, maybe something else is compromised also. You may need to do this for all of the hardware components of the device, or a particular hardware component of the device that cannot be changed without changing other components, etc. Right? But this is the high level. Essentially, you have a trusted device, and then you have a device that you want to trust. And if you want to trust it, you basically send a challenge, X, to the device. The device evaluates a physical unclonable function and sends a puff response, X. And the trusted device checks whether that puff response matches the previously recorded characteristics of that device. There needs to be a registration process of this device beforehand. Okay. And if the puff response matches what this trusted device expects, then the device is authenticated, and you can potentially, for example, execute a function or send some critical data. Because now you can trust that the assumption is that the device is now authenticated, meaning it's the same as what was installed when you actually registered the puff challenge response pairs. Okay. So what are the characteristics of the device that we want? Essentially, ideally, you want a runtime accessible puff, meaning you should, when you get the challenge, you should quickly evaluate the challenge to generate a response with minimal impact on the concurrent applications, right? Because it should not disturb what's going on in the device. And this way, if you actually do this quickly, you can protect against attacks that swap system components with malicious parts. And again, we also wanted to do this with DRAM because we believe it's a promising substrate because it's really ubiquitous in modern systems. Any kind of SoC has some sort of DRAM, right? And if you want trusted SoC, then you actually want to perhaps evaluate on DRAM as well. So this is not the first work on doing physical unclonable functions on DRAM. Prior works actually have retention-based puffs. You can guess what that is. Basically, it turns out if you actually don't refresh DRAM for a long time, you get a failure pattern in the cells. And that failure pattern is unique to the device. So this is one example of a puff. It's called DRAM retention puff. Unfortunately, based on everything we know about DRAM, you know that this is actually a very slow process, right? Because you don't refresh DRAM, and the evaluation of this puff takes a long time. We want a much faster puff. Yes? That's right, exactly. Temperature, VRT, DPD, exactly, yes. So the latency puff will be more reliable in that sense, you're right. Okay. Okay. That's right, but you read the paper, it's not as much dependent on the temperature. So you still need to actually have different temperature ranges. No question about that. Yes. We're going to talk about that, yes. So these are not the only characteristics. Yes, it needs to be, but it needs to be unique, basically. Two devices should not have the same. Yeah. Mm-hmm. Hopefully not. That's what you want, right? Well, if you do the challenge response in a nice way, you can basically maybe you do multiple challenges, right? And then it's kind of like balloon filter, right? In a balloon filter, you have a single hash function, you may get unlucky. If you get multiple hash functions, you get luckier and luckier, right? So it's the same way you can actually increase confidence. Yes. Yeah. Yeah. But that's a different problem, right? Man in the middle attack, you should be avoiding them in some other way. Yeah, you see what I mean? This is just a puff itself. But yes, the entire authentication protocol, that needs to make sure that the end-to-end is reliable. Yes. Yeah, it's a fascinating topic. I think that goes into more security aspects, etc. But yeah. It's called actually remote attestation. There's a lot of work in that area to make sure that remote attestation works. Okay, So going back, what are the puff characteristics that we want from an effective puff? So one is repeatability, meaning you have a trusted device that queries the DRAM device 0. You keep sending the same challenge, you should be getting the same response, right? This is not only it. You need diffuseness, meaning if you send different challenges to the same device, you should get different responses. This is actually important because you may want to test different challenges. And if this is actually one of the important things that helps DRAM, because DRAM space is very large, right? It could be maybe terabytes. It enables you to actually do a lot of different challenges. These challenges could be different latency parameters, for example, right? Okay, uniform randomness is important. This kind of addresses what you said earlier. You cannot use multiple challenge response pairs to guess another one. Uniqueness is important, meaning different devices should respond differently to different challenges. Maybe significantly differently, especially if it is probabilistic, as you mentioned. And there should be unclonability, meaning if you clone the device, well, you should not be able to clone the device, right? That's why physical functions are really useful, especially physical functions that are dependent on variation is useful, because even if you clone the device, clone the exact logic, you will not get the same function, right? Or, yeah. Mm-hmm. Mm-hmm. Yeah. Yeah, I mean, you need to have a registration process. That's true for any remote attestation process, though. Mm. But if you really want security, this is what you need to do, right? You don't do this for every device, perhaps, but when you really care about the security, this is something you do. Okay. Okay, so there's more analysis of these characteristics in the paper, and the paper actually covers all of these from the DRAM latency puff perspective. Okay, I think I've kind of discussed this, but we also need to have low latency and low system interference, and reducing latency is actually help in this case. So I've given you the key idea over here. The key idea is to compose a puff response using the DRAM cells that fail with a high probability. This requires a lot of profiling. So it's not just registering the device. There are a lot of system level challenges over here. So I think you guys are asking the right questions, but a lot of them are really like the full system security perspective, which need to be handled. But from the actually making sure that the puff is correct perspective, you still need to do a lot of profiling. So there's work involved in everywhere over here, but I don't think security comes without work. So keep that in mind. If you want to be secure, you have to put in the work. There's no easy way, I think, over here. There could be other ways, like you could register the device with actually, you could come up with different puffs, but all of them have the same problems, I think, in some way. So, and some of them compromise security. The puffs that don't have like this large challenge response spaces actually may compromise security. You may say, oh, why don't I have a unique identifier in the device, right? Well, that could be easy to forge, right? That's very easy to evaluate, very easy to actually set up also, but that's very easy to forge also. So that's why people have moved to this physical unclonable functions that are really dependent on variation, which fundamentally make the registration process hard also. Okay, so basically I think I've given you the key idea. The rest is detail in the end, but it's important detail. So temperature dependence, for example, is important. But one of the biggest benefits of this is really you can evaluate this puff with very, very low latency, regardless of temperature. So retention puffs, which was the previous state of the art, requires a lot of time to evaluate. And we evaluated actually in this paper. I'm not going to go through all of the details over here, but basically this is the latency puff. It's independent of the temperature, and it's always 88 milliseconds. You can read the paper as to why it's 88 milliseconds. It depends on how we actually do things. But if you look at the retention puffs, at lower temperatures, they require very high evaluation times. Like, I think this is, 10 seconds or something like that. Maybe 1 second, maybe 10 seconds, 5 seconds or something like that. And these are dependent on the manufacturer also, as you can see. And also, basically, in the end, we're about 2 orders of magnitude faster than the previous DRAM PUF with the same DRAM capacity overhead. So DRAM capacity overhead comes from basically what fraction of the DRAM are you using to actually generate these challenge response pairs. We limited ourselves to 64 kilobytes, but you could actually use larger if you want. Okay, I wanted to cover this because I think this is an interesting topic, and maybe there needs to be more done in this area. And this is a very quick summary that I'm not going to go through right now, but you can look at it yourself to summarize the entire paper with a small summary. But if you're interested, there's the paper. There's a talk that Jeremy gave. This was part of his thesis. And maybe there's more to be done here. Any other questions? No? Does anyone have a better PUF idea? So I should also say that, I'm going to say this later on, but everything we discuss is applicable to other technologies as well. SRAM, Flash, people have looked at PUFs in SRAM, Flash, people have looked at random number generators, people have looked at reducing latency, maybe not as much reducing latency, but certainly PUFs and TRNGs have been looked at in SRAM. I think the problem with SRAM is it's very small. So the challenge response space is very small in SRAMs, which again leads to some security issues that people have shown. With Flash, it's very slow. So DRAM is a nice place over here that it's big and also fast. Not as fast as SRAM, of course, unfortunately, but maybe fast enough in this grand scheme of things in the remote attestation case, for example. Okay, now we're going to talk about true random numbers. We've also kind of covered this, but essentially, Jeremy, while doing the PUF work, we also realized that you could generate random numbers nicely in DRAM. So this is his other paper. And the basic idea I've already given you, actually. Right? Basically, you can reduce the latency, and a cell's latency failure probability is determined by random process variation. And some cells essentially fail randomly when you reduce the latency to a particular level. These are called random number generator cells, and then you can essentially harvest their values by repeatedly accessing them. That's the idea. And what you would get is a random bit string if you keep repeatedly accessing a random number generator cell. If you want to generate a 64-bit random number, access this random number generator cell 64 times, for example. It would give you a random bit string. Or if you care about the latency, figure out 64 different random number generator cells and access each of them once in parallel, ideally, and get 64 different bits, and that's your random number. Right? So that's the idea. I've given you the idea. I'm not going to go through it more detail, but this paper, as well as the previous one, has nice animations. Just to show you that there's a physical basis to this, as we have discussed. Essentially, there's a ready-to-access voltage level that enables reliable access. So you can do a read over here. So there's a timing margin over here, clearly. There's a guard band. What we're going to do is we're going to change the parameters. So there's process variation. And because of that process variation, different cells reach the ready-to-access voltage level at different times. This is just one example. The spread is actually much larger than this paper, than this picture depicts. So there are clearly some strong cells, and there are some weak cells. Weak cells, as you can see, need more time to get to the ready-to-access voltage level. Strong cells need less time. Now, if you reduce the timing, you will get weaker cells will have a higher probability to fail over here. And the idea over here is to find the cells that fail randomly, that are not too weak, that are not too strong, but that are kind of at the edge at that level. And whenever you access them, you cannot predict whether they're going to fail or not fail. As a result, they're random, right? And we believe this is true random numbers because there's no reason there should be some, let's say, correlator to this process. It's really based on physical phenomena. It's based on the sense amplifier noise, bit line noise, cell noise, etc. So it's all noise that we cannot really model today. In fact, it's it's modeled randomly using Monte Carlo simulations. People actually use pseudo-random number generators to model these things, which may not really match the true randomness, of course. Yes. Yes. Yeah. Yes, yes, definitely. Definitely. If you actually find some other cells, for example, or if you change the timing parameters, some cells are truly strong, some cells are weak. And those are the things that we use for puff. Extremely strong or extremely weak cells that you select, and that's the unique signature. Okay. But here, in this case, we want really things that fail randomly at a given timing parameter. Okay, so that's the basic idea. Find cells, like these orange cells, that fail randomly. We don't want the high chance to failure cells. We don't want the low chance of failure cells. We want really the randomly failing cells, like 50%. And this requires testing, of course, again, profiling. You cannot get away from profiling. Okay, so basically we generate these random values by repeatedly accessing these random number generating cells and aggregating the data that we read, as I mentioned. And we actually run it, there's entropy characteristics in the paper. You can read the paper for more detail. And there are also statistical test suites that test for randomness, and these random number generators pass all of those tests. Granted, those test suites I don't think are very strong. I think there could be better test suites for these things. But entropy is always a good metric to measure. What is the entropy that you're getting? If it's 100%, and that will probably be a great random number generator, right? We're not at 100%, but we're close. Okay, so, and the throughput is high and the latency is quite low. And the power is actually quite low also. So these are some characteristics. And the paper has a lot more data, including the temperature dependence, etc. Again, I will not go through the detail. This is the executive summary. And I think this is a kind of a nice idea. This is based on testing, I know, hundreds of DRAM. Right, there you go. 282 LPDDR4 DRAM devices. So we actually built infrastructure to test LPDDR devices for this. And compared to, I think, previous best DRAM-based random number generators, we are, again, more than 2 orders of magnitude better in terms of throughput and latency. And you can read more about other random number generators in DRAM. A lot of them are, again, retention-based, etc. Okay, so this was published at HPCA 2019. But there was more work in this area, which I will cover. I find this area fascinating. That's why I want to spend some time over here. These are actually not changing the DRAM circuitry. This requires changes to the memory controller. But we're going to later talk about changing the DRAM circuitry a little bit. Not too much, because we won't have a lot of time. Okay, now you can watch Jeremy's talk. Let me see. I think I'll cover this and then we can take a break. So this is Ataberk's work. Basically, Ataberk found out that you could do better, essentially. Again, without changing the DRAM chips. But you could also change the DRAM chips to supply this function. So everything that we describe, as I mentioned in the memory-centric computing lecture, you could show DRAM chips are capable of something. The next step is really potentially showing that actually you could do that thing by putting it into the standard, for example, right? You don't necessarily have to violate timing parameters to do this. For example, this random number generation functionality could be very useful for processing in memory. And it could be added to the standard. This doesn't need to be violate the timing parameters and you get random numbers. Why not add it to the standard, right? Why not add this as a function of the DRAM, potentially? Maybe some different standard. Maybe it's a DRAM capable of computation standard. Okay, so let me give you the basic idea over here. I'll skip through some of these slides. Ataberk has very nice slides over here, but basically we improved our motivation over here, basically saying that we want random numbers for many things. For example, quantum computing, simulations, etc., actually rely on true random numbers also. But a lot of other things also require random numbers. And ideally, we would like to pay minimal costs for these random numbers. And we want high throughput in these. Okay. So essentially, one of the other motivations that we have is really processing in memory. So if you really want to have processing in memory, if you want to put security critical functions, for example, on the memory side, you really need some random number generation circuitry over there. And I think that's one of the main benefits of random number generation in memory. You could use it off the bat also, as we will see, or as we have seen in the D-range. So essentially, prior DRAM-based TRNGs are slow, including the latency-based ones that are not high throughput. But basically, this is the motivation that we have. Essentially, These are not TRNGs that I didn't mention, but retention-based TRNGs I told them. There's also startup value-based TRNGs. Essentially, what you do is you start up DRAM and you look at the failure of patterns, values. It turns out this is also random. People have figured that out. But if to be able to use this sort of random number generator, you have to turn off your DRAM, right, once in a while. So this is not a good way of generating random numbers. Does that make sense? So it's very interesting. So clearly the other ones are work. Essentially, we can get better entropy from DRAM rows with the method that I'm going to describe now. Okay, basically the key observation is very simple. We've seen multi-row activation in this course. In this paper, Ataberk observed that you could actually do quadruple row activation in real DRAM chips. And if you actually concurrently activate 4 rows, this gives you a random number. And this is kind of expected, right? For example, you activate DRAM rows that are initialized with conflicting data, 2 ones and 2 zeros. And this is 4 rows. And you activate 4 rows concurrently. Now, what value do you get? A random value, hopefully, depending on what is strong and what is weak, right? It really depends on which cells are strong, which cells are weak, and what is the bitline noise and the sense amplifier noise. So this is what it looks like, basically. Row 3, row 2, row 1, row 0. These are alternatingly 1 and 0. And you know this picture very well. Basically, what we're going to do is we're going to activate, pre-charge, activate, violate timing. It opens 4 of these rows, and we know this now well. And essentially, the sense amplifiers will be filled with random values because you don't know what to expect over here, right? And that's essentially what you get. You don't know what to expect. Okay, I will not go into a lot more detail because I've given you the key idea now. But there needs to be one-time characterization. Each sense amplifier needs to be characterized so that you get the entropy. You get the different entropy, 0 entropy and 1 entropy. If you want to know more about this, you can read the paper. And then you get the sum of each bitline's entropy. And then you initialize the rows to these 1 and 0s, perform the quark operation, and read the block. And then there needs to be some post-processing that we do to make sure we weed out, let's say, non-random parts, because there is some non-randomness also. But in the end, after this post-processing, you get a true random number. A lot of other works actually do post-processing also. Ideally, you would get random numbers without post-processing, but that may not be very easy. Because the reason is there are some areas in DRAM that are not necessarily random, right? As we have discussed. Some columns are actually weak. And in that column, maybe you get always 0, right? And you want to get rid of those things with this post-processing. Okay. So we studied this with 136 real DRAM chips. And there's a lot more data again in the paper. Ataberk did a lot of these studies with DRAM Bender, of course. And here are some key results. Essentially, this was this may still be the highest throughput random number generator. It outperforms the state of the art, which is DRAM latency to random number generator a lot. And you can actually get a 256-bit random number in relatively small time, 270 nanoseconds. This could be reduced, I think, but this is what the results suggested based on the chips that we've tested. With, I think, more channels, you can actually reduce that latency by generating more bits in parallel. Okay, it passes the NIST randomness test, but they're not that hard to pass, I think. And this actually is relatively low cost. There's little overhead. And there's also little storage overhead. Essentially, you just need to reserve a small amount of rows in a DRAM module to be able to do that. So entropy changes with temperature, but it remains stable for up to a month if temperature doesn't change. So you do need to do the profiling at different temperatures. So you need to find out which parts of a DRAM chip can be used for different temperatures. I don't think we can get away without that. That's true for also the DRAM latency to random number generator, D-range. And I didn't talk about that, but there's a lot of data in the paper that corroborates that. And this is the summary. Again, I'm not going to go through the detail, but this is everything we kind of talked about in one slide. Yes. That's a great question, yes. Now you should talk to Ismail because, well, Ismail, he's not here. Maybe online, find Ismail. Because, yes, that's a good question. Basically, in this case, the observation was that we used 4 rows because that's what we could do. But later we figured out that you could actually open more rows. You could do this with 2. You could do this up to 32. And actually, Ismail is a nice plot that shows that 4 rows is not the optimal. So you could actually get much better random numbers with higher numbers. In fact, there's even more potential than that. But if you're interested, talk to Ismail. But that's a great question. Okay, so that's the Quark TRNG. Another answer to your question is because Quark is a nice name. It doesn't work with DWAC or something else. Okay. Okay, so later works actually did end-to-end analysis of this, and you can find some information about that in Nisa's paper. How do you actually integrate these random numbers, not just Quark TRNG, etc., in a real system? This is based on simulation because we cannot change everything in a real system and memory controller, but you can take a look at this paper. And Ataberk's other work, FLY-DRAM, which we mentioned in the memory-centric computing lecture, actually shows that you could actually do derange in real DRAM chips, well, which was shown already, but you could also end-to-end evaluate it. If you remember this work, in this work, for example, we could offload the RAND function, random number generation function, to the memory controller, and you can actually get end-to-end results with that random number generator. And our measurements show that you could actually get random number generation with 220 nanoseconds. I believe this is end-to-end. So basically, you can actually use this infrastructure, this FLY-DRAM infrastructure, which is open source, and he has a lot of talks on that topic, to evaluate the goodness of the random number generator on a real application that's running on this RISC-V core in the FPGA. So this is really an end-to-end study. I don't think he ported the Quark work over here because this was done concurrently with the Quark work, but it actually does derange over here. And I think there's room for actually extend this. This was done, this FLY-DRAM work was done based on what we know a few years ago, and it takes time to develop the infrastructure. So today we know a whole lot more about what else we can do in DRAM. So extended this FLY-DRAM to a new infrastructure that can do, for example, different numbers of activations and generates random numbers based on different numbers of row activations could be very interesting. Okay, this is a good place to, I think, take a break, unless there's a burning question. So let's take a break for 15 minutes. What is that? Where does that put us? 15:35. And then we will finish this lecture and who knows, maybe start the next lecture. Is it time? Okay. Okay, let's see. I think here I'll mention one more work, which I think is interesting. So far, we've looked at works that actually violate timing in DRAM to generate random numbers. I believe there's more to be done in this area, especially based on what we know today, especially activating many rows in different subarrays, for example. But there's also another work that I think is quite interesting, which is modifying the DRAM, underlying DRAM, to do these things better. I will not go into a lot of detail over here. This is called codec, fine-grained control over DRAM internal circuit timings. This is actually useful for multiple different things, not just security, but it actually has a lot of benefits for security, as the executive summary that I will go over will show. But I will leave the details to you to understand in the paper. This paper was rejected 9 times before it got accepted to ISCA in 2021. Maybe I should look at the acknowledgement section over there. You can see that it was first submitted to HPCA 2018. And I think the basic idea is actually quite nice and clever. Over time, it became a framework of changing the internal timing parameters. So there's some internal timing things. Like there are some parts in DRAM that are exposed to the DRAM controller, but there are some parts that are not exposed. For example, you cannot directly enable the sense amplifier, right? There's no way you can do that today. You send a command saying pre-charge, and that does something through the pre-charge circuitry. You send a command activate, and at some point the sense amplifier gets enabled. The idea of this work is to directly manipulate those timings so that you can actually generate random numbers or destroy data nicely internally. Okay, so maybe I'll go through this kind of small font summary. But basically, the timing of DRAM operations is fixed. As a result, it's very difficult to implement new functionalities and optimizations. This is kind of not intended also, right? Nobody wants you to implement new functionalities and optimizations. That's one of the reasons why paper is kind of rejected multiple times, right? Even researchers don't want you to do something new. Clearly, DRAM manufacturers don't want you to do something new because they want you to actually just access data. They don't want you to discover what's going on and implement something new. So our goal in this work was to provide control over internal circuit timings to enable new functionalities and optimizations. So basically, what are these timings? If we can actually externally control and change at a fine grain, for example, enabling the word line, enabling the sense amplifier, enabling the pre-charge logic, asserting and deasserting some of these internal signals, you can do a lot of things, as this paper shows. So there are 2 variants over here. One is codec sig. It generates signature values, meaning kind of randomizes things potentially. And codec det that generates deterministic values. And you can do this at low latency. So what are the applications? Very quickly, we can do physical unclonable functions in a better way. We know what physical unclonable function is, right? So basically, key idea is to assert the timings such that you set the circuitry in a way such that you get some variation. And that variation is really unique to the device. I may mention this later on. And we find out that this is two times faster than the best state-of-the-art DRAM puff. So basically here we have more control. We're not violating the latencies, but we're actually changing the timing such that you exploit the variation that happens in the bit lines, okay? So the second part is over here, cold boot attack. We kind of talked about that, right? If you have your memory, and your memory can retain data. A lot of the cells in your memory can retain data for very long, actually, as we have known before. Hundreds of seconds at low temperature. If you actually cool it down, it can retain data for many, many days, maybe years. So cold boot attacks say, steal someone else's memory, make it extremely cold, preserve it, and then plug it into your own device and read it. That's the idea. So there are works that have shown that you could actually reconstruct a lot of things in a system if you are able to do that. But this requires physical access, of course. So how do you prevent cold boot attacks? You could encrypt data, of course. Hopefully that will solve the problem, but encryption could be expensive, right? Memory encryption every time may be expensive. The idea over here is to destroy all data at power on using codec. So you basically change the timings, and if you change the timing, that bit line, for example, you set the bit line to VDD over 2, and then that bit line drives everything to some random values, and we will see that in a little bit maybe. So that's the idea. It can be done in multiple ways. Different types of timings can actually change it, but this way you can actually set the value in a particular subarray to all random values. This way you can destroy the data. Make sense? Okay, so we find out that you can actually do this much faster than the state-of-the-art mechanisms like row clone. There could be other things over here like reliability, performance, energy optimization that we didn't explore. So let's take a look at these timings quickly. For more detail, I'll refer you to Louise's presentation. But for example, you have the word line that controls the access transistor that connects the cell capacitor to the bit line. Today, you cannot directly control it. Activate eventually activates the word line, but you cannot only control the word line, right? So we're going to enable mechanisms to control the word line. There's also sense amplification circuitry over here, and then there are two transistors. There's a PMOS, and then there's an NMOS amplifier. And if you can control them, actually, you can enable some different functionalities. And we suggest that you actually control those sense N and sense P circuitries. And then there's the equalization signal or sense amplification signal, essentially. Well, not sense amplification, but EQ signal that controls the pre-charge unit that essentially equalize the bit line to a VDD over 2. So the idea in this paper is to really enable control over these internal timings. Now, let's say what you can do. This is one example. Well, I guess I don't have the other example, but you can read it if you're interested. Essentially, this is the example of PUF, physical unclonable function. This is kind of a complicated picture, but it's not that complicated. But the key idea is to amplify a DRAM cell that you set to the pre-charge voltage. So basically, this is the value of the bit line initially, VDD over 2. This is the capacitor value. What you do is you assert the word line just enough so that the capacitor becomes VDD over 2. And then you start the pre-charge signal. So a capacitor is initially set to 0 or VDD. You raise the word line signal enough such that the capacitor becomes VDD over 2. And then you raise the pre-charge signal. Now, if you do this, the final value of the cell is really the pre-charge voltage over here. I mean, does that make sense? Because really, the VDD over 2 circuitry is really the pre-charge circuitry is driving the cell value, right, in the end. This is actually one way of setting the value to VDD over 2, as you can see. I don't know if this is more or less reliable than the other way that we have done, but it needs to be investigated. And then in the next activate command, the sense amplifier generates a signature value that depends on truly random process variation, because it's really sensing VDD over 2s in the cells. Does that make sense? So at that point, you really get a unique signature of the device. You could use this for random number generation as well. That is not explored as much in the paper, but you could use this as a physical unclonable function. So I think the key takeaway is if you're able to carefully control these internal signals like word line setting, raising the word line, and raising the equalization signal in the pre-charge, you can enable different functionalities. In this particular case, it's really writing a VDD over 2 into a cell. And then activation after that enables your true random variation. And using that true random variation, you can do either random number generators or you can do physical unclonable function. These two are actually two sides of the same coin. If you're able to get some true random number variation, true variation, you could exploit this as a PUF, assuming you can get uniqueness and all the PUF characteristics. And you could exploit this as a random number generator as well, assuming, again, you can get some files that are sailing randomly. In this particular case, I believe you can do both. And the paper shows it with PUF. Any questions? People are thinking. So if this is done, then you don't need to violate the timing parameters, as you can see. Of course, another way of doing it would be making the violation of timing parameters standard, but it won't give you as fine-grained control as this one does. Now, how do you know how long you keep the things, like how long do you need to wait to assert the word line voltage? And how long do you need to wait to really assert the pre-charge EQ signal? That is really empirical in the end. All of this is done using circuit simulations in this paper. So that requires some modeling, characterization, etc. Okay. So this is a way where you can actually destroy the cell values. Another way is actually really in DRAM row copy, right? This is a bit slower, but maybe with if you're able to copy one row to many rows, this is actually also a quick way of destroying the cell values, right? I think since multi-row copy was not known at the time we did the codec work, it'd be good to compare which one's better today. And I don't know which one's better actually. We compared to row clone, but we didn't compare to multi-row copy. So maybe with a multi-row copy, if you can extend multi-row copy, especially to the subarray level, with one, let's say, multi-row copy command, you can destroy the content of an entire subarray. That's a very quick destruction. You can potentially do it across all of the subarrays of DRAM, right? And this way, you can actually get better cold boot or faster cold boot attack prevention. So there needs to be more investigation, I think, to see which mechanisms are better. And you know this work is, we discussed this in the memory-centric computing lecture. Okay, any questions? Yes. Okay, yeah. Yeah. So today, I don't think there's any mechanism to detect, but the way we describe in the paper, I don't know if it's in the slides, probably not in these slides at least, but basically, when you power on, you can detect that you're being powered on. At that point, you basically initialize everything to whatever, random number, 0. Yeah, that's our suggestion here. Today, I don't think it's done that way. I don't believe, unless you design a very custom DRAM board where you really care about these cold boot attacks. But if you lose your DRAM today, it's subject to cold boot attacks. If someone implemented codec, I think it would be secure, more secure, let's say. But I don't think it's implemented today. That's a very good question, though. You need a way of detecting, not necessarily a cold boot attack, but basically detecting that something is happening, something fishy is happening, right? Exactly. Yeah, if there's a very quick mechanism to destroy all the data every boot, that should hopefully solve the problem, right? Or yeah, but it needs to be a quick mechanism because nobody wants to wait for your DRAM to be initialized for a long time, right? Okay, any other questions, thoughts? These are good thoughts. Maybe you'll come up with better mechanisms. Okay, I'm not going to talk about reducing refresh latency. There's work in this topic. We've talked about overlapping the refresh latencies a little bit in the last lecture. I'm going to flash those. I will talk about one thing that's also interesting that was done by Hassan. Again, very quickly, I'll go through these executive summaries. Basically, in this work, our goal was to reduce average DRAM access latency with no modification to existing DRAM chips, similar to some of the other works. But this is going to exploit another observation. There are multiple observations here. So if a DRAM row is highly charged, it can be accessed with low latency. And you know a DRAM row is highly charged when you restore the charge, right? So when you access the row, and then at that point, at some point, the charge gets restored. And at that point, it's really highly charged. And we also find out that a recently accessed row is likely to be accessed again, meaning that there's some row level temporal locality in the applications. So if you know all these three things, maybe you can come up with a mechanism like this. Basically, the idea is to track recently accessed DRAM rows. And if a row is really recently accessed and you're going to activate it again, use lower timing parameters. Why? Because again, the hypothesis is that you have accessed it recently, you restore the charge recently, the cells have a lot of charge in them. So you don't really need a lot of time for those cells to be sensed. That's the idea over here. And again, in the ideal incarnation, this is low cost and this doesn't require modifications to DRAM. And we see significant performance benefits and energy reductions by doing so. I like this idea. It turns out it doesn't, because there's some internal circuit timing that happens in DRAM, you cannot really show this in real DRAM chips. And you can read the paper for more detail as to why you cannot show that. But I think that technically the idea works, except it's not easy to show it in real DRAM chips. And this is Hassan giving the lecture, so you can learn more about that. Okay, there's more works on partial charge restoration beyond AL-DRAM. AL-DRAM actually triggered more work on partial charge restoration. This is not the only work, but this is one of the works that we have done. If you're interested, you can take a look at it. And as I mentioned, there's work on parallelizing refreshes and accesses, which doesn't completely reduce latency of a single access, but really overlaps the latency of multiple accesses. So this is still useful. And you all talk about HERA, which does it on real DRAM chips. There's more work on power consumption, which I'm not going to talk about. This is actually a very interesting area. I think we need to look more into power consumption of chips in general and understand power consumption characteristics under different use cases, like processing in memory, reduced latency operation, high voltage, low voltage operation, etc. And this work takes a stab at it. This is work that we did with NVIDIA. NVIDIA was quite interested in understanding this for obvious reasons. They do a lot of memory, clearly. And we had the infrastructure, so they came to us, can we do these studies? And we did those studies. And this actually builds a power model. You can take a look at it. I'm not going to talk about that, but this required a lot more infrastructure building that was done by multiple bachelor students plus multiple other people. If you're interested, you can take a look. But this is a power model, so you need a lot of measurements. Guy can tell you more about this also if he hasn't forgotten. Vampire still haunts him at night, probably. So maybe he has forgotten about the vampires. Yeah, I'm just kidding. Yeah, it does. You cannot forget. Okay, so it's so powerful. It's good experience. Building these infrastructures give you a lot of, let's say, experience and also courage to build even more infrastructure that is more capable going into the future. But yeah, I'm skipping over it, but there's a lot of work that goes into building this infrastructure, multiple years and some failures along the way. Okay, and the DRAM vendor. Okay, so I think we're almost done. Essentially, I'll summarize. We have talked about low latency, but we also kind of included power and energy just a little bit around it. I think this is very important going into the future. We've looked at two different ways of reducing latency and by tackling two different fundamentally reasons of high latency. One is the design of memory chips, and the other is how we actually treat memory chips today. You can combine both also, of course, which we have not done, but you can imagine that. So I think we can really reduce memory latency more. This requires a change of mindset because clearly you can do a lot of these today, but it comes at a cost. So reducing latency needs to come at a cost. Maybe there needs to be a better room for actually reduced latency, maybe slightly reduced capacity chips. But of course, I think the other takeaway from all of these works, I think without exception, is you cannot reduce latency without changing the controller. You can, basically everything we have done requires some change to the controller, either small or large. In many cases, relatively large. I have talked about some outstanding problems. Again, this requires intelligence in the controllers. Okay, I think we exploited some principles, but I'm not going to talk about that. Especially with latency, we exploited these principles a lot, better than worst case design and heterogeneity. So ideas are applicable to other technologies. I mentioned that. I'm not going to talk about these, but there is work in exploiting similar ideas like process variation or even temperature in different technologies like flash memory, but also phase change memory. We have done, these are some of our works, but there's also other works by other folks that you can read in the references. We're going to talk more about these when we talk about SSDs and emerging memory technologies, but not necessarily we're going to focus on latency. We're going to focus on other issues in SSDs and emerging memory technology when we go to those lectures. But keep in mind that a lot of these ideas are very general. even though they're demonstrated on DRAM, they could be applicable to other technologies as well, with some slight changes. And there could be other ideas, of course, in other technologies that could be found that are independent of DRAM, because other technologies have some characteristics, as we will see, that are not found in DRAM. So here, but we're not exploiting a lot of technology-specific characteristics. For example, partitioning the bit lines is useful for any technology in the end. It reduces latency, it reduces energy. Okay, that brings me to the end. As I expected, we don't have time for the next lecture, which will start tomorrow. But we do have time for questions if people have questions. If not, we can be done early. No questions? And everybody's ready to be done early. Okay, let's be done early then. I'll see you tomorrow. We'll cover memory controllers tomorrow.